Okay, hi. Good morning, ladies and gentlemen. I'm Pierre Morandi, and I come from Rhopoint Instrument, and I'm here to present to you our new instrument, which is the TAMS, which stands for Total Appearance Measurement System. And you can see the TAMS right here as well, and I will take it later in my hands. So, what is the TAMS and what was the beginning of the TAMS project? Initially, the TAMS project has been inspired by Volkswagen. That was a requirement from Volkswagen to get a new instrument to define the perception, the quality of car coatings, etc. So in fact, we've been doing this project with Volkswagen, but then AUDI and Porsche, and also many paint suppliers. And this project today is, as you can see, exclusively distributed by Konica Minolta. So please do not hesitate to pop in at the Konica Minolta stand. So what are we speaking about? We are speaking about surface finish appearance. When we look to a car coating, the paint, what's happening? We got a perception, and then we feel a certain quality or harmony feeling. So the final idea is to get a new instrument to define or to predict the customer's perception and preferences. Is this paint nice or not? Is the comparison between two paints okay or not? That's the question we want to ensure with the TAMS. So in fact, when we look to a reflective surface, subconsciously we have two focuses. The eye is focusing on the surface. So first, focusing on the surface, and then we can see the texture, the size of the little waves, etc. But then, almost at the same time, the eye is also focusing on the environment, on the sand, on the light, the trees, everything around the paint. Okay. And at the end, with those two focusing, we can have a global idea of the perception that we get looking to a surface. And also, because we are never static, we move around the paint, we can feel the perception evolving thanks to those two focuses at the same time. And we get a kind of perception of waviness and sharpness and dimension, etc. So in fact, in the brain, there's a lot of mechanisms which at the end bring to, oh, I like this paint, or I don't like this paint. So what's happening in the brain, that's the thing we try to understand, put in the instrument, and let's tell the instrument, is the paint good or not? That's the challenge. So here is the TAMS, as you can see, in two hands, and internally, camera, screens, battery. So basically, the TAMS is working in the same way than the eye is working. Let's try to grab the reflection of something. When I look to a car, I see the reflection of my environment. When the TAMS is working, the TAMS is displaying some pattern internally, and the camera will grab the reflection of those patterns in the same way than the eye is doing. So basically, we display some black and white patterns, and we grab reflected images. Okay? So same than the eye, first focus on the surface, and then we got a second focus on the target screen, target image, right. And then in the TAMS, we use different technology like optical transfer function, line deformation analysis, and phase measuring deflectometry to, at the end, try to characterize the surface and then try to compute with those values the human sensation values. So technically, what is the TAMS doing? The TAMS is computing four main characteristics, four characteristics, sub-characteristics, the contrast, the sharpness, the waviness, and the dimension. Why do we do that? We do that because we think in the perception of the human eye, those are the four characteristics mainly involved in the brain mechanism. But at the end, we want the TAMS to be able to give only two main values. The quality, is this paint nice or not? Do I like it or not? And the harmony, do those two surfaces match together or not? two main values to define the human feeling and predict it. So during this study, we've done a lot of job about the correlation with the visual perception. We have now a new quality control possibilities, and also very, very important with only two values and easy to understand value, we can improve the communication in the supply chain. And we also have a better understanding about the appearance itself of a paint. So during the study, we've done a lot of panel ranking and multidimensional scaling with Rhopoint, us of course, but also VW, Audi, Porsche, the paint suppliers. We've done some tests on automotive finish, so very nice paint, or transport finish with Scania. We've used metallic, colors, piano finish, a lot of samples. About the algorithm, I've been developing the algorithm for almost everything, and I had a quite important input from VW, but also Audi, thanks to the multidimensional scaling study. So at the end, it's a 4 years project with more than 500 paint panels, 10,000 measurements, etc. So let's try to speak a little bit about what the TAMS is measuring. So first, the TAMS is measuring the contrast. So you have here on the top left kind of screenshot of the TAMS instrument. So you can see the contrast value, which is a percentage. So what is the contrast? Usually on a very low contrast surface like a white, the contrast is very poor. So even if the quality is very, very high, you are not very able to see the reflected scene. You've got here an example of an orange surface, 64%, and here an example of a black surface, a very, very deep contrast, 97%. The contrast is very important because we know that if the contrast is very high, the paint quality will have to be very high because the eye is easily able to see any little defect or the waviness phenomenon or anything. So first, we compute the contrast. The second value that we compute is the sharpness. So what is the sharpness? The sharpness basically is the ability to a surface to reflect, to reproduce some very fine details. You've got three examples on the bottom. You've got a very poor quality surface with a sharpness about 50%. As you can see, I am in the street in London, and I can have a look to this nice building, but the quality is very poor. Because the surface quality is bad, the sharpness is bad. And with a very high quality paint, I would be able to see very, very fine details on the reflected environment. Obviously, the sharpness is a very important value involved in the perception of the quality of the paint. So to compute the contrast, we are using the optical transfer function, and depending to the distance we look at the paint, we can have a kind of detail reflection level or a haze effect if the sharpness is bad. So, as I said, to compute the sharpness, we use the optical transfer function. Basically, the idea of this technology is to display many fringe patterns with different size, and if the panel is with a very high quality, the panel will be able to reflect properly both large pattern and small pattern. So basically, the idea is to compute the evolution of the contrast reflected from large pattern to very fine pattern. So you've got three examples here. You have the evolution of the fringe pattern frequency, and then you have the contrast value. You can see that for very large fringe pattern or very low frequency, it's easy to get a high contrast. But then, when the frequency is increasing or the size is very small, it is hard to reflect properly the pattern. So that's an excellent transmission. That's a middle transmission. That's a very poor transmission. We get the integration of this optical transfer function curve, and we can get the sharpness value. The third value that the TAMS is measuring is the waviness. So the waviness is the way the surface looks wavy, or the way the reflected image is completely distorted by the wave at the surface. The waviness that we measure try to define the way it's flat or non-flat. So if the waviness is very, very low, we have a very flat surface and a very nice reflection. We can almost not see any waves. But if the waviness is very high, very, very high, a lot of waves, we have a lot of deformation on the surface, and we can easily perceive waviness, which is absolutely terrible for the quality of the paint and for the final appearance. To do that, we are using a proper algorithm called the line deformation analysis. Just some word about this algorithm. Basically, the TAMS is displaying some absolutely straight lines, and then the TAMS try to find the lines and analyze the deformation of those lines, and then we compute a fast Fourier transform to get the energy inside those lines and know more about the waviness value. So thanks to a final integration, we finally have the global waviness value of the paint. Okay, to finish, the fourth value calculated by the TAMS is the dimension, also called dominant structure size. What is the dimension? When we look to a wavy surface, we can see many waves, but at the end, the brain would be able to say, what I see is small waves, or middle waves, or big waves. We've got 3 examples here to show you. We have here some quite small waves, middle waves, and big waves. So this is a major step forward because that's very important for the harmony of a car. We can have 2 surfaces with the same contrast, the same sharpness, the same global waviness, but if the dimension is not the same, if one surface is with the small waves and the other one big waves, the harmony is terrible. So that's for that purpose that the dimension is absolutely required. To compute the dimension, we are using the well-known phase measuring deflectometry algorithm. Just some word about the phase measuring deflectometry algorithm. We display many fringe patterns shifted. Then with a specific algorithm, we compute the full curvature map on the field of view of the TAMS. Then we compute a global FFT of this curvature map to try to know more about the kind of fingerprint of the surface. What is the definition of the surface in terms of wave? We get a spectra, which is the raw spectra seen by the instrument, and then we transform this raw spectra to be fitted with the human perception. So by using the contrast sensitivity function, we go from the raw spectra of the instrument to the correlated spectra with the eye. And then at the end, we can easily see where is the peak. So where is the main information about the dominant structure size? This is here, and we get 3 mil, 2 mil, 5 mil, 4 mil. Anyway. Right, so we've got contrast, sharpness, waviness, and dimension. Even if the human eye is not able to realize that all of those things are happening in the mind, at the end, what you can say is that I like this pen or I don't like this pen. So the first very important value computed by the TAMS is the quality. To compute the quality, we are using the sharpness and the waviness value with a scaling and with proper weighting. Because we know that at the end, in the brain, those 2 values are mainly involved in the quality. If the quality is very high, that's because the sharpness is very high, very nice reflection, no haze, proper details and everything. And the surface is very flat, almost no waviness. High sharpness, low waviness, very high quality. So this is a very interesting value because at the end, with one number, you can easily sort different quality in the paint process or for different cars or anything. The second very important value computed is the harmony. So the harmony is this time using the waviness and the dimension, because 2 surfaces will be very visually different if the waviness and the dimension are 2 different. So we compute the delta waviness and delta dimension compared to a reference surface. We scale it, we combine it with proper weighting, and we get the harmony value, which is 1 if the harmony is acceptable. It means 50% of the people would accept the difference and 50% would reject. If the value is below 1, that's good. If the value is above 1, that's bad. The harmony would be statistically rejected. Okay, at the end, we've got very new instrument with a new philosophy, but also thanks to the optical methodology inside, we've got an instrument very versatile and ready for the full painting process control. So body painting, of course, as I said, but also we've got some very interesting preliminary results for e-coat and fillers, but also stamping, molding, steel, aluminium. So we could have, in the future, we could have only one instrument for the whole chain of the paint, rather than the existing technology is not that able. Okay. So possibilities, matte surfaces, query shape recognition, 2D gloss analysis, inline robotic sensor because the measurement is static and not rolling. Many interesting possibilities. Just some word about the technical specification. We've got a aluminum body, a color IPS screen, touch key. We've got a push and start measurement. It means I can turn on the push and start function. My instrument is ready. I just push on the car, read. I push, I read. I push, I read. It's very, very easy, very quick, very accurate as well. We've got a quite high spatial resolution, 34 micrometer per pixel, a good field of view, a very interesting acquisition time and computation time below 4 seconds, very good battery life, a lot of measurement possibility, good connectivity, USB, SD card, Ethernet for robotic implementation, RFID for car body recognition with a tag, and a good data export possibility. Well, just some word about what is the TAMS doing and what is the existing technology doing for the same purpose. The TAMS is measuring quality and harmony thanks to contrast, sharpness, waviness, dimension, dominant structure size. And those values are easy to understand and easy to discuss about. Rather than the existing technology is mainly speaking about long wave, short wave, WA, B, C, D, E, DY, dullness. And at the end, that is not that easy to understand and to discuss about. And that's the reason why initially this project has been initiated by VW, because they wanted something more simple, more easy to understand, and more fitted for what they need. Right. Some word about the advantage. It's easier. We have no surface damage risk because the measurement is static. We could even have a non-contact measurement. We could have that. We could easily implement for body control on a robotic system. We've got a full correlation with the perception, better chain supplier communication, a lot of data for in-depth analysis. Okay, and as I said, a very versatile and powerful instrument for many, many applications. That's the end of my presentation. Thank you very much.